So here is another important concept that we already kind of implied. We said how much warming or how fast the warming happens depends on various feedbacks, and we looked at past climates, and temperatures have changed at various levels, and CO2 has changed as well. And we said with ice ages, glacial, interglacials, CO2 goes up and down as well, and methane and N2O also go up and down. So you know that there are these feedbacks in the system. Climate sensitivity is a concept which says that we keep increasing carbon dioxide from a reference level to twice its level at some rate, and then we just fix it there. And all these feedbacks at various time scales, including weathering time scale, which is a very slow time scale, will all get adjusted, responded, vegetation, ocean circulation, atmospheric circulation, glaciers, everything, and then you get a certain warming over a long time scale. That is called climate sensitivity. If you double CO2 and keep it there, at equilibrium, what temperature change we will get? This is very critical concept because now we are changing CO2, we are increasing CO2 and other greenhouse gases. So we want to know what the system is capable of doing in terms of warming. Okay, so that's the basic idea. So here we are looking at the idea of perturbation, atmospheric temperature changes, whether this could be orbital perturbation, greenhouse gas perturbation, and we have a positive feedback to atmospheric humidity, and that increased warming is going to send upward long wave radiative flux, which is a intrinsic negative feedback because of the Planck function, or Stefan Boltzmann law, sigma t to the fourth. The question, of course, is we can increase greenhouse gases very rapidly, whereas the sigma t to the fourth is a slow time scale change. So it cannot work as fast as we can increase greenhouse gases, which is why we have global warming. Otherwise, heat would be constantly lost and we would have nothing to worry about, right? So this is the concept of a net feedback. Here is a positive feedback, here are two negative feedbacks. If you multiply all of them together, you get a net positive feedback in the system, which is why we have global warming. But things are not so easy to compute all the time, because when we have very complicated network like this, it's not always easy to say whether we have a net negative feedback or net positive feedback. And if it is really a net positive feedback, that means the warming will get accelerated, and which is possible to some extent, because if we are melting glaciers, albedo is decreasing, more and more energy is being kept in the system, faster and faster warming will happen, and sea level will rise, and so on and so forth. So here we are, temperature change. This is time in years, so you are starting with a reference temperature of 0, and you are increasing CO2 here. This is the time of doubling CO2 here, so you have increased it by 1% per year. So in 70 years you have doubled it, and then you fix the CO2 and see what happens. So the CO2 is fixed here, but because CO2 is going to move through the system, as we saw, ocean, atmosphere, vegetation, and temperature, and so on, the warming will continue even though you stopped emitting here. So the warming will keep going and will eventually reach equilibrium. So this is the additional warming commitment with forcing stabilized at 2 CO2. What does it mean? That means we are emitting CO2 at some gigatons per year. Even if we magically manage to stop all the emissions today, because we have put already so much into the system and the system is still equilibrating, the warming will keep going, and that is called committed warming. So this is the additional warming commitment we tend to make, because CO2 is a slow inertial gas that has a very long residence time. Okay, so this is the temperature you are going to get, and this sensitivity here is 3.5 degrees centigrade. That's what determines this final global warming accomplished if we freeze the CO2 emissions at double. During this time, this warming is called transient climate response. This is the equilibrium response, because here CO2 is still changing and temperature is still rising. The same thing happens when you raise it to 4 times. So this is time to CO2 quadrupling, 140 years, and transient response keeps increasing the temperature. And if you stopped emitting CO2 here, then you have additional warming here, again committed additional warming. Okay, so how do we determine these sensitivities? Not very easy at all, but best estimates are made using models and past known forcing changes like ice age to non-ice age, or pre-industrial to industrial, and so on. And usually you end up with a range, with the most likely range, very likely range, and likely range, very likely range, and most likely range. Okay, the trouble of course is also that the climate sensitivity is not constant in time. So for the instrumental period, which means from the Industrial Revolution to current, the estimates are here, quite a large range from likely, very likely to most likely. Current mean climate state shows this kind of sensitivity, which is smaller than here. Climate models indicate a sensitivity that is here, because models have various unknowns, deficits, misrepresentations, etc. The last millennium estimated range of climate sensitivity is here. Volcanic eruptions have this kind of climate sensitivity, and this is from data for last glacial maximum and for models millions of years ago, combining different lines of evidence. What does it all mean? Essentially, that means that our climate is sensitive to perturbations. They can be directly perturbations from orbital parameters, or because of greenhouse gas changes, or it can be because of a combination, because orbital changes drive glacial changes, which drive greenhouse gas changes, as we saw. And the sensitivity doesn't need to be the same in every situation, because it may depend on how the perturbation propagates through the system, and which feedbacks dominate, which time scales dominate, and so on. Right? Ice ages are very long. The glacial stages are very abrupt and short, so obviously climate sensitivities are not symmetric either. So this is a very critical and important concept, and yet quite difficult. And just last year, the latest estimate of climate sensitivity was put out by some 20 to 40 experts in the field. This is critical because when we use models to make projections for the future, we have to be sure that we are representing the system properly, because we know the perturbations we are making, like the radiative forcings we saw, and we need to see how the system will respond in terms of how much warming will happen and how fast it will happen. So this is obviously a very difficult challenge. So here are the climate feedbacks and sensitivity to doubling the CO2. If there is no feedbacks, we expect just the change of long wave radiation to give us a sensitivity of 1.2 degrees centigrade. But the when you include carbon cycle and ice sheets, oceans, vegetation, we are looking at time scales again here. So let's start here. Clouds, water vapor are in the range of years. Snow, ice, and upper ocean are in the time scale of decades. There is an estimate that was made by a committee led by Charney in the 1970s, which gave a range of 2 degrees to 4.5 degrees C as the climate sensitivity. The number remains almost the same, but maybe it's higher at 3 to 6 degrees centigrade. But what is the difference is, at that time we didn't have all the knowledge we have now. So the uncertainty is still there, but now we are somewhat more certain about where the uncertainties actually come from, and that's very useful as well. So atmospheric composition changes, ozone, aerosol, and dust are in the range of years to a decade or so. Methane in the decadal range. Vegetation changes can be centuries. Oceans take millennia because it's deep and moves slowly and keep the heat for a long time. Ice sheets, of course, take multi-millennia to build up. So here we are. Carbon cycle, again, to equilibrate will take a very long time. So that also has multi-millennial time scales. So altogether, we may be in this range of 3 to 6 degrees centigrade, but you will find much more on this from the IPCC report, and there are some very nice papers written on what the climate sensitivity is, and so on. Here, the idea is to give a brief introduction, and hopefully this helps. Okay. Again, Wikipedia, Carbon Brief, Skeptical Science, Climate Central. There are many good websites which give introductory level information on all these concepts. So anytime you are curious or not very clear based on my podcast, please go and brush up or add more details from all these other sources. Okay, so this concludes this chapter on theories. We'll now move to carbon in the next chapter. Okay.